This is your presenter Asloob Mudassar, and I am presenting slide number 83 of the course on laser physics. Question is, consider a two-mirror resonator consisting of two spherical mirrors of radii of curvatures R1 and R2 with 2A1 and 2A2 as the respective diaphragms. The mirrors are separated by a distance equal to capital L as shown in figure 83.1, that is in this figure. The caption is a typical two-mirror resonator consisting of spherical mirror 1 and spherical mirror 2 with the diaphragms 2A1 and 2A2 respectively. The radii of curvature of the spherical mirror 1 and 2 are respectively R1 and R2, and the two mirrors are separated by a distance equal to capital L. Discuss equivalent lens guide geometry. Represent field after one round trip in terms of the field at the input plane, which may be regarded as point source. Also derive an expression for the cavity resonance frequencies. So you see that in this question we have to calculate the field at the first mirror is known, and you know that it is in the form of a point source as stated over here in the question. So the field at the spherical mirror 1 is a point source, and this field will travel towards the mirror 2 and then it will be reflected back towards the mirror 1. So it will complete one round trip, and we have to find the field after one round trip. But we cannot apply the Fourier optics to calculate the field in one round trip in a very simple way. So what we need to do is that, as suggested in the question, discuss equivalent lens guide geometry. So we shall use an equivalent lens guide geometry, which will be a replacement of the figure of the system shown in figure number 1, and then we calculate the field using that lens guide geometry, and we have to calculate the field after one round trip in terms of the field at the input plane, which is regarded as the point source. And of course we have to find an expression for the cavity resonance frequencies. So this is the question, and you see that this is our geometry, and we have to find out the field in one round trip. But we shall not be using this one to calculate the field after one round trip, but instead we shall be using this geometry. So the caption of this one is lens guide geometry equivalent to the geometry shown in figure 1, that is in the previous figure. So here you can see that we have lens 1 and lens 1 on the left hand side, and on the right hand side of the middle lens, which is marked as 2. The lens 1 on either side are identical with the diaphragm equal to 2A1, and the lens in the middle has a diaphragm equal to 2A2. The focal length of lens 1 and the lens 1 on either side of the lens 2 being equivalent lenses has a focal length equal to f1, which is related to r1 by 2, and the focal length of the lens 2 is f2, which is related to r2 by 2, and the separation has been shown to be 2L. L is the separation between 1 and 2, and then from 2 to 1 on the right hand side we have the same separation equal to L. So actually this forms a one round trip. So when the light will travel from the lens 1 to the lens 2 in this lens guide geometry, then of course it will complete one round trip as suggested in this figure. You see that this mirror 1 has a diaphragm 2A1. So when the light will reflect back from the spherical mirror 2 and will reach back at the mirror 1, then of course the mirror has a diaphragm 2A1, and this has been shown as a replacement of the two lenses on either side of the lens 2 and marked as 1. So this lens 1 on either side of the lens 2 has a diaphragm equal to 2A1, and you know that the total separation is equal to 2L. So let's now try to answer this question. Consider a two-mirror resonator as shown in figure 1, this one. Assume that a field is launched at mirror 1 to propagate towards mirror 2 and then to propagate back towards mirror 1. This back and forth, that is one round trip of the field, can be visualized through an equivalent lens guide geometry as shown in figure 2, that is in this figure. Now we shall, rather than solving the problem using this figure, we shall solve the problem using this lens guide geometry. So we shall be calculating the field from the lens 1 to the lens 1. Lens 1 on the left hand side to the lens 1 on the right hand side. Assume that E prime x as x1 E prime of x1 y1 comma 0 with the field at the diaphragm 1, that is at z is equal to 0 plane. So this is over, this lens 1 is located at z is equal to 0 plane, and the lens 1 on the right hand side is located at z is equal to 2l. And we are assuming that this E prime of x1 y1 0 is the field at the plane 1, at the z is equal to 0 plane, where x1 and y1 are the transverse coordinates at the plane z is equal to 0. The corresponding field at z is equal to 2l plane is represented by E prime of x comma y comma 2l, because here z is equal to 2l, and the coordinates at the second lens 1 are represented by x1 xy, where x1 y1 are the transverse coordinates at the lens 1 on the left hand side, and xy are the coordinates are the transverse coordinates at the lens 1 on the right hand side. This field can be linked or connected with the input field through the Huygens-Fresnel integral as given. So we are connecting the field at the output of lens 1 to the field at the input of lens 1. So E prime of x y 2l is equal to e to the power minus iota 2 kl, and the double integral over the surface area of provided by lens 1, and then integrands are E prime of x1 y1 0 multiplied by kappa of xy semicolon x1 y1, and then we have dx1 and dy1 as the integral variables. So the integral, the Huygens-Fresnel integral connecting the two fields, that is the output field with the input field, is shown in equation number 1. The integration is over the aperture 1. Kappa is known as the propagation kernel. To solve the integral, we assume that the input field to be a point source, that is, so our input field is represented by a delta function, because we are assuming that our input field is a point source, that is a delta function. So E prime of x1 y1 0 is represented by delta of x1 minus x1 prime comma y1 minus y1 prime as shown in equation number 2. Which means that the delta function is located in the input plane at the coordinates x1 is equal to x1 prime and y1 is equal to y1 prime. So this is the location, that is the center at which the delta function is resting. And substituting E prime from equation number 2 into into the integrand within the equation number 1, we solve, and you see that then E prime will be replaced by delta function. So you have a delta function over here, and using the property of the delta function, that setting x1 is equal to x1 prime and y1 is equal to y1 prime, since we are specifying, we are fixing the value of x1 and y1, so the integral will be eliminated and only the variables will change. That is, kappa will have the coordinates, that is x1 and y1 will be replaced by x1 prime and y1 prime in the kappa, and the rest of the integral will vanish out. So we have E prime on the left hand side as a function of xy 2l, and then multiplied by e to the power minus iota 2 k capital L, then multiplied by the kappa function having the coordinates x comma y, and then of course x1 prime and y1 prime. So actually this kappa is actually linking the information at the coordinates x1 prime and y1 prime to the coordinates at the position x and y. And you know that x and y are the positions at the output plane, and x1 prime and y1 prime are the variables at the input plane. And kappa is actually a function that provides the image at the output plane of the field at the input plane. So if you have a delta functions at the input plane, then kappa will give you the image of that delta function of that point source at the output plane. If you want to know further details about this integral and the solution of these integrals, I would refer you to consult my Fourier optics course, which is also listed on, which is also have many slides on the YouTube. So you can consult one of the slides and you can find further details about such an integral. So solving that integral, we have the output E prime of xy 2L is equal to e to the power minus iota k 2k times L, and then we have the kappa, which is x comma y and x1 prime and y1 prime. Thus kappa when multiplied by e to the power minus iota 2k into capital L is the output field in response to the input field as point source. Now let's assume that in the given geometry the field is reproduced in shape after one round trip. So consider this statement that the field is reproduced in shape. You see that when in this case, when the field will travel from mirror 1 towards mirror 2 and then will back and then will travel back towards mirror 1, then of course the field leaving the mirror M1 towards mirror 2 and then receiving the field from mirror 2 to mirror 1, these two mirror has to be these two fields must have the same field, must have the same shape of the field. So this is what we have written over here. Field is reproduced in shape after one round trip. So the output field should be equal to the same as the input field. But of course there are some factors, for example sigma prime and e to the power minus iota 2k into capital L. E to the power minus iota 2k into capital L takes care of the phase when the light will travel the total distance equal to 2L. And sigma prime can be set equal to, sigma prime is equal to sigma mod prime into e to the power iota phi is a complex constant, and sigma mod is less than 1 because it cannot be greater than 1 because output cannot be greater than the input. So at the value of the sigma prime mod should be less than 1 is due to the loss in beam due to diffraction. Because when the diffraction will take place, some part of the beam will be lost, and of course the value of the sigma prime mod will be less than 1. Thus equation number 4 takes the following form. So we are now substituting sigma prime is equal to sigma mod into e to the power iota phi into equation number 4, and after collecting the terms of interest, we are now have the field in equation number 5, that is e prime of x y 2L is equal to sigma mod multiplied by e to the power minus iota 2kl plus phi, and then we have the initial field e prime of x comma y comma 0. So this is what we have given, we have included the value of the, or we have included the role of the sigma prime in writing equation number 5 from equation number 4. But we are using equation number 4 in equation number 1. So this is our equation number 1, and on the left hand side we have e prime of x, y and 2L. So we are replacing this e prime of x, y, 2L with the value from equation number 4. And then after simplification we get equation number 6. So on the left hand side we have sigma prime into E prime of x y comma 0, and then on the right hand side we have the integral with the integration limits evaluated over the surface 1 of the plane z is equal to 0. Then we have E prime of x1 y1 0, and then kappa of x comma y and x1 y1, and then dx1 and dy1 as the integral variables. This integral is important. This is known as the Fredholm integral. Its eigensolution is represented by E prime of Lm as a function of x, y, 0, and the corresponding eigenvalue by sigma prime Lm. And sigma and the absolute square of sigma prime Lm is a factor by which the intensity is changed after one round trip. And 1 minus sigma mod square of and 1 minus absolute square of sigma prime Lm then gives the round trip fractional power loss due to diffraction. So this is what we have briefly stated about the Fredholm integral. We are not going to solve this integral, but we know that that the solution of this integral will give you the field at the output plane, but in principle after one round trip. You see that E prime of x comma y comma 0 will be the initial field, and of course after one round trip this would be the same field. So after one round trip the field, we want that the field is reproduced in shape. So this is what the integral states, that after one round trip you have the same field as the initial field on the left hand side of this integral, that is E prime of x comma y comma 0. So the solution of this integrals will give you the eigensolutions and the eigenvalues. So it means that the field after one round trip is given by equation number 6. Now we are going to rather solving this integral. Because this will be beyond the boundaries of this lecture that we solve this integral, but we are going just to give the important points relevant to this integral. The round trip phase shift can be represented as delta phi Lm. This is the change in phase shift that will be in one round trip, that's equal to minus 2k capital L plus phi Lm, where phi Lm is the phase which was initially present, and after one round trip the change in phase was equal to delta phi as given on the left hand side. But you know that delta phi Lm is equal to minus n times 2 pi, because we want that the field should be reproduced in phase, in shape, and this requires that the phase should change by 2 pi or integer multiple of 2 pi, as we have given that delta phi Lm is equal to minus integer minus n times 2 pi, where n is an integer, and this is the requirement for a self-reproducing beam. So that is, if you want to reproduce the same beam after one round trip, then delta phi should change as integral multiple of 2 pi. So equating the two values of delta phi, we have minus 2kl plus phi Lm is equal to minus 2 pi n. Now substituting a k by 2 pi into nu over c, we obtain the cavity resonance frequencies as, so nu we have used a subscript Lmn, so we have nu Lmn is equal to c over 2l, multiply within the parenthesis we have n plus phi Lm over 2 pi. So these are the resonance frequencies in the resonator, and you can see that it involves the length of the cavity and the two pass in the length of the cavity as far as the figure 1 is concerned, and 2L in as a single pass when we are using the circuit shown in figure number 2, figure number 2, which is a length guide geometry. Okay, so we have now obtained the formula for the cavity resonance frequencies, and phi Lm, you know that is the initial phase, n is an integer. So all the things are explained. So we have explained how the field after one round trip is given. This is given by equation number 6, and the resonance frequencies are given by equation number 7. L and M determine the order of eigen solution whereas the integer n gives the total phase shift of the beam in units of 2 pi. So I think that the answer is complete. This is the end of slide number 83.